Hi everybody! This video is going to be talking about how to draw electron orbitals. You will need a couple different color pencils. I'm going to use red, orange, green, blue, purple, but you can use any 5 colors that you like. You could use pens, markers, color pencils, but the color coding is going to be really helpful. We're going to take some notes over here on this side and draw some pictures as we go. So first, an orbital is an area an electron is most likely to be found. Sometimes people call it a probability cloud. In middle school, you're usually taught that the electrons go around the nucleus in little rings like the Bohr model, and that's not exactly correct. So it's a little more complicated. They do travel around the nucleus, but not in nice little rings like planets around a sun. They're going to be in a little bit more complex shapes, and those complex shapes is an orbital. So we have energy levels. We're going to have energy levels 1 through 7. That's what we know about these days. In a few years, who knows, maybe they discover something different, but for now, 1 through 7. The lower the number, the closer it is to the nucleus. Most energy levels, not all of them, but most energy levels can have multiple orbitals. I've heard all sorts of analogies for this. The one I like is that you can have a building, which is like your atom, and the building can have energy levels, which are the floors. Some buildings only have 1 floor, single-story buildings. Some can have multiple floors. So atoms can have 1 energy level, 2 energy levels, all the way up to 7 energy levels. Just depends on the atom. Next, inside each energy level, you might have multiple orbitals. So our building analogy, each floor might have multiple rooms on it. So if we have space, so if there is room, if the energy level is big enough, we can have an s orbital. We can have 1 of those. We might have p orbitals. We can have up to 3 of those. We could have a d orbital. We could have up to 5 of those. And we can have an f orbital. We can have up to 7 of those. Someday maybe they'll find out there's more than that, but for now that's what we're going to use. The names of these orbitals are funny because the names are just letters. So the name of the S of this orbital is S, P, D, F. Kind of funny that we name them, but those are these. Next, we're going to see the number of electrons that can fit in each orbital. And at the most, we can have 2 electrons maximum. So, going back to our building analogy, if the atom is our building, we can have different floors inside our building. The floors can have different numbers of rooms, but each room is only ever allowed to have 2 people in it. So we can have lots of energy levels. The energy levels can have different numbers of orbitals, but each orbital only has space for 2 electrons at a time. After that, it's full. So we have lots of floors with different numbers of rooms, but each room can only hold 2 people. So sometimes it's easier to count the electrons in little batches called sets. We may not care about each individual orbital. We may care more about all the electrons that are in a P shape or all the electrons that are in a D shape. So sometimes that's a little bit easier to talk about. So if we have S, P, D, and F orbitals, one orbital each can hold 2, so that's a total of 2 electrons. We can have 3 p orbitals at a time. They each can hold 2, and that's a total of 6. A d orbital, we can have 5 of those at one time. They each hold 2, so that's a total of 10. If we can have 7 f orbitals at a time, and they can each hold 2 electrons, that means 14 can fit all together. So this is the number of electrons in a set of orbitals. It's like saying if we want to know how many people all together can be on a floor at one time, what would the total number be? Sometimes that's a little bit more useful of information. So all the things that I've kind of boxed or underlined in green are really key pieces of information that you'll need to kind of memorize. So we need to make sure that we know that an orbital is where an electron is most likely to be found. We don't know for sure that's where it is. There's no rule that says it can't be somewhere else. It just means that it's very likely to be in this area called an orbital. We can have 1 to 7 energy levels. There are 4 types of orbitals, 4 different shapes, categories that we have. We have an S category, P, D, and F. In each energy level, at the most, we can fit 1 S, 3 P, 5 D, and 7 F orbitals. Each orbital can only have 2 electrons. So if I wanted to count them by a set, an S can hold 2, a P set can hold 6, a D set can hold 10, and an F set can hold 14. One of the things that kind of trips people up is they misread a question. If I ask how many electrons can fit in an orbital, the answer is always 2. If I ask how many orbitals I have, your answers are going to be 1, 3, 5, or 7. If I ask how many electrons can fit in the set of the orbitals, your answers are 2, 6, 10, 14. So just be a little bit careful that you're looking at the question closely. Make sure that it's not asking about one orbital at a time versus all the orbitals at a time versus asking how many orbitals you have. So just be a little bit careful there. So now let's start drawing the shapes. The one here, the big number in front, is the energy level. You tell people which floor you're going to in the building, and then the shape, the type. So you tell people you're going to the first floor and you're looking for the room that's the S shape. The nice thing is the S stands for sphere shaped. That's how I remember it. Because it's in the first energy level, it's going to be pretty close to the nucleus. So pick your first color. You do not need to have art skills, I clearly do not, but try to shade it in so that it looks a little bit more 3D. We don't want to be drawing a circle, we want to be drawing a sphere. So for the next box, it's in the second energy level, but it's still an S shape. So because this is a higher energy level, we're going to be further away from the nucleus, but we will still be sphere shaped. So I'm going to pick my second color, and I'm going to draw a bigger sphere around the nucleus. And same thing with your new color. Try to shade it in so that it looks a little bit 3D. The second energy level is big enough that we can fit an S orbital and we can fit P orbitals. The first energy level was so small that we could only fit this singleton here. Only one tiny little orbital can fit. But because the second energy level is much further from the nucleus, we have a little more space so we can fit a few extra orbitals. So this is the second energy level, P-shaped. I was always taught that it's petal-shaped, like flower petals. And this little subscript here is telling you which axis it's on. So this is going to be lined up on the x-axis. So it doesn't matter which one is which, X, Y, and Z, but label them so people know. It's going to look like two flower petals that connect with each other in the center. And we want to make sure that we are making it look 3D. So they're really more like teardrops that are connecting. They're not flat like a flower petal. They're more teardrop shaped. Sometimes I've heard people call them peanut shaped. If you had a peanut in a shell. But I was always taught petal, so that's what I still call it. But try to make them look 3D. The next one, the second energy level is big enough that we can fit another orbital. It's also going to be petal-shaped, but this time it's going to be lined up on the Y instead of X. So new color. It's still the same distance from the nucleus because it's still in the second energy level. Do your best to try to draw it the same shape and size as this one, but it can be a little tough. and try to make it look 3D the best that you can. The second energy level is big enough that we can fit another orbital. This time it's in the second energy level. It's still going to be petal shaped, but it's going to be lined up on the Z. So try to draw it same size, same shape as before, but just line it up on the different axes. Try to make it look somewhat 3D if you can. Now, this energy level has run out of space. It's not big enough for any d orbitals. It's not big enough for any f orbitals yet. And p orbitals, we can only fit 3 at a time. So we're kind of full on this level. After this, we have to go to the third energy level. And then we'd be able to fit more orbitals, starting over, drawing another S, more p orbitals, then maybe we could fit some d orbitals. Then that would be full. We'd go to the next energy level. We'd be able to fit an s orbital. We'd be able to fit some p orbitals. We'd be able to fit some d orbitals. And then we'd finally be big enough to be able to fit some f orbitals. So for now, this one is full. What I want us to do next is realize that all these orbitals are existing at the same time. They're not one or the other. They're all existing together. So we're going to redraw everything all superimposed on top of each other so that we can see that even though we know there's these discrete areas inside our atom with these specific shapes, because they're kind of all superimposed on each other, what we end up with when we're done is going to look like a big brown blob by the time we're done. So I have my 1s, my 2s, my 2px. Here comes my 2py. Now I have my 2pz. All kind of superimposed, and it's starting to look like a big brown blob. And the overall shape that starts to appear is rather spherical. And so when we imagine atoms as these spheres, it's because with all these shapes overlapping, if we didn't know better, if we didn't know that all these intricate shapes were inside, it would look rather spherical. Now let's try to figure out which atom this is. I can figure that out by counting the electrons. I had an s orbital with 2 electrons inside. I had a 2s with 2 electrons inside. I had a 2px with 2 electrons. I had 2py with 2 electrons. And I had 2pz with 2 electrons. If I add those all up, I end up with a total of 10 electrons. And because you're not told otherwise, you can assume that this is neutral. So 10 electrons is going to tell me that there are 10 protons, which means this is neon. So in an atom of neon, we end up with the electrons buzzing around, kind of like bees around a beehive. They move randomly all over the place in crazy little directions, and they tend to fall in these shapes. So 2 electrons will buzz around here, 2 electrons will buzz around in this shape, 2 electrons will kind of buzz around in this funny shape, 2 more electrons can buzz around in this direction, and the last 2 electrons, will buzz around in this shape. So when they're all together, the 10 electrons look like they're all buzzing around in crazy random directions, but we know that they're actually buzzing around these individual orbitals. Now imagine if you had 7 energy levels with all 5 different shaped orbitals, in all those energy levels getting further and further and further from the nucleus, the shapes getting crazier and crazier. D orbitals and F orbitals are so strange, I won't ever make you draw them. Only S and P will I ask you to draw because those ones are reasonable to draw. You know, they get crazier and crazier, bigger and bigger, more and more and more complex. But really, we can break it down into the fact that we're going to have 7 energy levels, 4 different shapes, 2 at a time, and at the end, it looks like a big brown blob. Alright, here we can see a picture of all the orbitals. I will ask you to draw an S orbital. I will ask you to draw P orbitals. The D and the F orbitals, as you can see here, are so strange that I'm not going to ask you to draw them. We have 5 different shapes for the D orbitals. We have 7 different shapes for the F orbitals. A little bit too strange to draw. So as long as you can draw an S and a P, you're good. As long as you know there's 1 S, 3 P, 5 D, and 7 F orbitals per energy level maximum, then you're good. This is the last thing I wanted to show you. I really love this picture of an orbital because it really conveys a little bit more information about how we know what the shape is. So an orbital is not a tangible object. It is not something you can reach out and touch with your hand if the atom was big enough. It's really just us drawing a picture of where we think that electron might be. So imagine you had a camera and you could take a picture of an atom with an electron buzzing around. And each time you take a picture, you can see and plot a little point of where that electron was found. So you keep taking pictures over and over, and you keep putting new dots on your paper every time you find the electron, over and 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 over. And what you're going to notice is that more often the electron can be found in certain regions of space. So certain areas will get more dots placed because you found the electron there more often. And that's because the electron is more likely to be found in this region. And so they kind of decide, well, most of the time it's found in this area, 90% of the time. So let's just draw a boundary and say that inside here is the shape. So this is my orbital. Most of the time, my electron will be found inside this shape. So you just keep putting more and more dots on your paper, and you can see we start to get a sphere shape. This would be an S orbital. So I like to show this picture because I think it gets across the idea that these are not tangible objects. And I think that's really important. We call them probability clouds because it's where we have a high probability of finding that electron. It doesn't mean the electron can't be over here or way over here or off the screen somewhere. It's that this is where it's most likely to be found. All right, everybody, I hope that's helpful. Bye.